All right, we're covering 2-7, curve fitting with linear models. Note we're skipping 2-6. We will get more into transformations later in the year, but we're not going to be doing it in this unit. I'm putting the warm-up on the board because if you're doing this, reviewing this video lesson, you're going to want to have this in your graphing calculator so you can practice the linear regressions. So we are using a graphing calculator today. Here's a list. This would be list 1. This would be list 2. Press Stat Enter on TI 8384, and that gives you your set of lists to put data into. All right, so this is 2-7. We're going to fit scatterplot data using linear models with and without technology and use linear models to make predictions. Linear models, linear regressions are extremely useful. We used them quite a bit in the company where I worked. We were in the research department, gather data, and then see if we can make a linear model using that data. So very useful concept. So researchers such as anthropologists are often interested in how two measurements are related. Statistical studies of the relationship between variables is called a regression. So it's a really fancy word, and it just means you're comparing two different data points or two different pieces of data. So you can use a scatter plot to plot one variable with respect to another, and it helps you understand form, direction, and strength of the relationship between two variables. So correlation is the strength and direction of the linear relationship between two variables. So here are the correlations that we're interested in. You can see this roughly looks like it's a line going upward. So since it's an upward line, that's where that means it has a positive slope. This one, and you can see it's not nearly as tightly related as the first one, but this one you could kind of fit this line in between the data. It's downward. It has a downward slope, so it's going to be a negative correlation, kind of a weak correlation, which we'll see in a little bit. And this, it just looks like random dots. There's no correlation. So if there's a strong linear relationship between two variables, a line of best fit or a line that best fits the data can be used to make predictions. A line of best fit can be called a trend line. So I've here they've drawn the line of best fit for you on this one, and here I've kind of drawn a line of best fit. And once we have that, I can make predictions for data points that I haven't actually collected in my data set just by using that line. All right, let's look at an example. Albany and Sydney are about the same distance from the equator. Make a scatter plot with Albany's temperature as the independent variable. Name the type of correlation, then sketch a line of best fit and find its equation. So we're going to plot the data points. So here's Albany's temperature down here. It's a little hard to see. And then Sydney's temperature is here. So it's Albany versus Sydney. And if you look at it, it's pretty tight set of data. So you're going to try and find a line of best fit. So it says sketch a line, do the best you can, use a straight edge so it's actually a line and not a squiggle of some kind. And they've made this line of best fit, and it really does look like it goes through the data pretty well. So that is our scatter plot. Next, identify 2 points on the line. So for this data set, you might select, and they've selected 64, I think it's this one. Oh, 35, sorry. 35, which is this one, and 85. So let me get rid of this line, or this point. So these are the 2 points, 85, on the line. So it doesn't necessarily need to be one of the dots, but it has to be on the line. 85 and 41. So 85 and 41 is this point here. We know how to write linear equation using 2 points. We find our slope. So x1, y1, x2, y2, we get a slope of negative 0.46. And then if we pick one of those points and plug it in for point slope form, so they've taken this point, plugged it into the equation, simplified, so distribute and then add your 64, and you end up with this linear equation, which is a model for that data. So an equation that models the data is y equals negative 0.46x plus 80.1. And this is really useful. Now if I want to find out what Sydney's temperature would be if Albany's temperature is 10 degrees, so right here I can guess it's going to be about 76 degrees. So it's now I can make predictions for any data item, any temperature that I would like. All right, the correlation coefficient R is a measure of how well the data set is fit by the model. So if we looked at that last set of data, you could see how tight the dots fit into a line, and that means that my model is probably pretty good. As we saw in a previous slide when we had the negative correlation, but all the dots were kind of far from the line, that's not going to be as good a model. It's not as going to be reliable. So we want to know how reliable the model actually is, and it's done using a correlation coefficient. And this is way too small, I'm thinking. I'm going to push this up a little so you can see it. So what this slide is telling us, the correlation coefficient R is always going to be in the range -1 to +1. If R is equal to 1, it's a straight line and a positive slope. So if I had dots that pretty much look like a straight line with an upward slope, we're going to have a correlation coefficient of 1. If the correlation coefficient is 0, it's going to be random. That means there's absolutely no correlation between the data. So that's this case. And if it's -1, it means we're going to have a very tight correlation, or the dots are going to make a straight line, but it has a negative slope. So this would be R equals, an example of R equals 1, R equals -1. And they show you here. And then you have all the things in between. So R equals a -0.95. It's a pretty good line with a downward slope. R equals -0.6. Again, you could fit some kind of downward slope line, but it's not nearly as good a model as this one right here. R equals 0, really, you're hard-pressed to figure out whether you'd have a upward slope or downward slope line. It's just kind of random data. Really, you can't make a model from that. And here's an upward slope, not that tightly correlated, but somewhat correlated. And this has a correlation coefficient of 0.95. Very tightly correlated data with an upward slope. So the correlation coefficient tells you whether you have a positive or negative correlation and whether it's a strong or weak correlation. We're not going to calculate this manually, but we can calculate it on our graphing calculators. So we calculate it the same way we're going to calculate our linear regression model, and I'm going to show you that in a minute. But you need to make sure that it gets calculated by making sure that it's in the right mode. So in order to make sure it's in the right mode, you're going to press second on, which gives you the catalog, and then you arrow down to diagnostic on, hit enter twice to turn it on, and this makes sure that it will calculate your correlation coefficient. So I just did a manual linear regression. Our calculators do one as well, and they do a little bit better job they have a more complicated algorithm for actually calculating the linear regression model. So to create the linear regression model on the calculator, first you have to have your data in, which is what you did for the warm-up. You put two lists of data. Those are the two data items that you want to correlate. and you're going to go to the linear regression, which is Stat Calc 4 linear regression on your TI 83 or 84. And for the data that I just talked about, the Sydney and Albany temperatures, if I entered those lists into my calculator, did my linear regression, it's going to give me A and B as these. This is what you plug into y equals ax plus b. So this is your slope that you would plug in here. This is your y-intercept. So this gives you your linear regression model, which is just the equation of the line of best fit for that data. So, having said all that, what you need to do then, here's the data that you put in. This is Anthropologists. They use the femur or thigh bone to estimate the height of a human being. This is the table that you put in. So I want you to do a manual linear regression. So pick 2 points. You want to do a scatter plot. So actually, I should say, do your scatter plot. Draw your line of best fit. And then pick 2 points on the line to create your linear equation. So I want you to create your linear equation manually. Then I would like you to use your linear regression function on your calculator and see what the two equations, how far apart they are or how close they are. So when I did it manually, I got this. The linear regression gave me this, and this gave me a correlation coefficient of 0.986, which indicates very strong correlation. So this was not too far off. The difference between the manual and the linear regression it's going to be different most of the time, and sometimes, depending on which points you pick, it may be very far off. So the last thing we'll do is actually use this data, because after all that work, you want it to be useful. So let's say a man's femur is 41 centimeters long. We want to predict the man's height. So we can do that using our linear regression equation. So here's our equation. It's telling us that the height is roughly 2.91 times the femur plus 5404. So we're going to plug 41 in for the femur length, and that tells us the height would be about 173.35. So linear regression is very useful. You now have 2 ways of creating linear regression models. This is your homework. Please bring questions to class.